Okay, so I want to finish going over this worksheet. You guys will finish the problems, but I just want to go over. So we did the graph for this one. You should do these graphs yourselves. And then you should finish up the graph on this one, on number 4. This is kind of the idea here that we have here, but just go ahead and finish up that section. To evaluate the following, what you want to do is use the unit circle. And most of you know how to do this. I think we had the unit circle on our other worksheet, on our first worksheet, but remember we filled it all out. And so what you want to do for any of these is you think of 7/3 pi and you go to where that is. So 7/3 is 6/3 plus one more third. So it's going to be the same as pi over 3 because 7/3 pi is like 2 1/3 pi. So you go around the circle to here and you're at 2 pi, so it's 1/3 more. And the ordered pair at pi over 3 is shorter in the x direction than it is in the y direction, so that means it's 1/2 in the x direction and √3 over 2 in the y direction. And then cosine is the y coordinate, so this will be 1/2. And you should be able to do the rest of those in a similar way. The only one that I'd like to kind of point at is for h, make sure that you're adding the arguments together before taking cotangent. You can't distribute cotangent, so you can't take cotangent of one and then add it to the cotangent in other. That is no. Okay, so let me go ahead and erase that so it isn't there. Okay, you cannot distribute. So you want to do inside the parentheses first. For this next problem, we have basically a pretty basic setup, and I want you guys to kind of work at it. And what you're going to have to do to solve this is because you're going to use trigonometry, obviously, because there's angles involved. So what you want to do is you want to look at the two different triangles the two different right triangles that are here. And even though I didn't mark it, let me see. So that big triangle, even though I didn't mark it, is a right triangle. And then you'll want to look at this triangle as well. And between those two, you should be able to figure out the length of x. So, number 7, a laser beam is to be directed toward the center of the moon. So here's the moon. And we're here on Earth somewhere, and we are directing the laser at the center. And then, but the beam strays 0.3 degrees. So here is the beam strain. It's going to be impossible to write to scale because 1/2 degree is really small. You get the idea. How far has the beam diverged from its target when it reaches the moon? So the important part of this one is to make sure that you're setting your right triangle up. So if we're looking at this, we have a right triangle. And just make sure you get your lengths right, and you get your, you're going to use like tangent of theta, where theta is this 0.5 degrees equals opposite over adjacent, which should be easy to do. And then the radius of the moon is about 1,000 miles. Will the laser beam strike, or will the laser beam strike the moon? So we're looking for this, how far it diverged, and then you're going to figure out whether or not that number is less than 1,000, and whether the person hit the moon, or we did. I guess that's us hitting the moon. Okay, number 8. So I do want to go over this one because at least the setup for this one. This one, the algebra is going to take a minute, but you guys can all do it. Okay, to measure the height of cloud cover in an airport, a worker shines a spotlight upward to get at an angle of 75 degrees from the horizontal. So here's the clouds. Here's the ground. 600 meters away. Hold on. In order to measure okay, so I'm gonna drop a perpendicular here from the cloud because this is the height of the cloud cover. And then we're over here, or we have an observer is over here 600 meters away. with the flashlight. This is 75 degrees. And, whoops, let me see. Let me reread it. To measure the height of a cloud cover at an airport, a worker shines a spotlight upward at an angle of 75 degrees from the horizontal. So the angle that I think I'm going to throw in this other person. An observer 600 meters away, 45 degrees. So I'm going to go ahead and change this one to 45. Sorry about that. Just because it looks more like a 45 degree. And then the 75 degree is a bigger angle. So I'll put that one over here. So we have an observer on either side. Find the height of the cloud cover. Okay. So you guys can do this on your own. The 600 meters is from here to here. I'll help get you set up a little bit. And we want the height, but we're also going to need to call this distance something. I'll just call it x. And so what we need, because we have two variables and we're going to end up having to use them both, is we're going to need two equations. Basically, we want the height of the cloud cover, so we just really need to solve for h. So we need a relationship between h and x, which we can get with this right triangle, and then a relationship between h and 600 that we can get by setting up that right triangle, and then putting them together we should be able. So I'll give you one of them, and that will be that the tangent of 75 degrees is equal to the opposite over adjacent. So that'll be h over x. And then you can do something similar with the 45 degrees, and then you can put them together, solve them, and finish up. Okay. This particular problem, just so you know, a lot of people, here's the thing that it doesn't say. An observer we have two observers, right? We have somebody with the 75 degree angle, and then the observer that's 600 meters away could technically be over on this side, okay? So the way that you could set up this problem, two different ways, two different answers, but do it the way that I did it, okay? Don't do it the other way. I just wanted to point out that the way that it's written doesn't really specify which scenario that we have, so. For number 9, I want you to find the values of the trigonometric functions of theta from the information given. And for these ones, I wanted to review this because you always want to draw the triangle. Oops. I'm going to draw a right triangle. Oops. I guess I can correct it here. Or not. I'm going to draw a right triangle. My triangle is really cheeseball, but that's okay. So cotangent of theta, that is going to be the reciprocal of tangent, which is opposite over adjacent. So it's adjacent over, this is theta, over opposite. Okay, that's what cotangent is. And the reason we have to draw the triangle is because these aren't coordinates on the unit circle. Okay, so the trigonometric ratios will be proportional to other circles, but they aren't unit circles. So the distance here of the radius is not 1. So you find it by doing your 4 squared, your Pythagorean theorem. So we get 17. Technically plus minus, but are always positive, okay? So when we do these triangles, sometimes the way I drew it actually kind of puts it into the second quadrant, which isn't necessarily what you want to do if you're doing it to that sort of scale or to that sort of proportion. But you do need to we also actually need to talk about this right here. If sine is less than 0 and sine corresponds to the height, then that means this one's negative. And in order for the cotangent to be positive, they both have to be negative. So that way it's negative over negative, which still gives us positive. And then the radius, you always want to choose the a positive distance for the radius. That's just a convention. It'll make everything work out. And so then sine is going to be your -4 over root 17. Whoops. You can rationalize these denominators if you like, but it doesn't matter if you do or don't. That's fine. So finish off the rest of those trig functions. And this problem was just to remind you that not all not all triangles are going to fit into the unit circle. Number 10 is really just calculator work, okay, and converting degrees to radians. Remember, 180 degrees is equal to pi. So you should be able to convert from radians to degrees by just replacing pi with 180, and you can convert from degrees to, if I have 190 degrees, 180 degrees is equal to pi, and so this will give you your radians here, okay? And then if you have sine of an angle, then you do arc sine. Make sure your calculator is in degree mode for here, and in radian mode, you'll get a decimal approximation for the radians. For number 11, this is a cool problem because it's a historical problem. Eratosthenes of, I think it's Cyrene. I shouldn't try to pronounce things at this point. Go ahead and read the problem, and what you're going to use is you're going to use arc length formula for this one. Go ahead and read it and set it up. It's not actually hard to set up because when you have a circle, the arc length is at the length of this arc right here. We call S. And it's just r theta, theta in radians. Theta has to be in radians. If you put it in with degrees, the formula doesn't work because radians are a proportion of the circle, okay? And so the only way you're going to get the arc length is if you have it in radians. Okay, so this one's actually in a pretty simple problem. Requires walking 500 miles in the desert, but okay, that's it. This will be, I'll post it so that you guys can turn it in by Sunday, hopefully, and there might be another one up soon. Thank you.